So question 1, a school guidance counselor examines the number of extracurricular activities that students do in their average grade point average. The guidance counselors say the evidence indicates that the correlation between the number of extracurricular activities a student participates in his or her grade point average is close to 0. A correct interpretation of this statement would be that, in this case, letter D is going to be your correct answer. The key here is that they're talking about correlation. And when we look at this answer, there is no relationship between the number of activities and the grade point average for students at the school. A 0 correlation is very poor, and it means there is no correlation. Remember, the correlation number can go between -1 to 1. The sign on it tells you the direction of the data. The number talks about the magnitude or how strong it is. Anything close to 1 is good. Anything negative means the data is moving downhill or has a negative slope. Anything positive means it has a positive slope. Number 2, the British government conducts regular surveys of household spending. The average weekly household spending in pounds on tobacco products and alcoholic beverages for each of 11 regions of Great Britain was recorded. A scattered plot of spending on alcohol versus spending on tobacco is shown. Which of the following statements is true? The best answer in this case is going to be letter E. The reasoning behind that says the observation in the lower right-hand corner of the plot is influential for least squares regression. And they're talking about this one. Remember, any outliers in the direction of the x-axis are going to have more influential impact on things as correlation and slope than any outliers in the y direction. Therefore, this particular point is our most influential one. Part A is stating that this is an outlier, and it probably really isn't. Again, there is no test that we can do. For Part B, there is clear evidence of a negative association. Clearly, there's a positive association that we see here. Because of this outlier, if we were to draw our line of best fit, keep in mind it's going to draw that line down toward it, so it would be a little less steep, but it's still positive. The equation of the line actually could not be this because this shows a negative slope. This data, again, has a positive slope. And the correlation of being 0.99 means it's a positive slope, which is correct, but this is an incredibly tight correlation. There's definitely a lot more spread in here. Number 3, the fraction of the variation in the values of y that is explained by the least squares regression line of y on x is, now by definition, they're talking about r squared, and r squared, remember, is called the coefficient of determination. So as you look at these choices, you don't actually see that as an option, but you do see the square of the correlation coefficient. It's very important to know the definition of r squared, or again, the coefficient of determination. I've seen a variety of free response questions where you are required to write out what it means, or I have seen multiple choice. Remember the difference between r squared and r? R is going to be our correlation coefficient, which is only for linear regressions. And again, as we talked about earlier, that tells us direction and strength of how linear our data pattern is to form a line. Number 4, an AP statistics student designs an experiment to see whether today's high school students are becoming too calculator dependent. She prepares 2 quizzes, both of which contain 40 questions that are best done by using paper and pencil methods. A random sample of 30 students participates in the experiment. Each student takes both quizzes, one with a calculator and one without, in random order. To analyze the data, the student constructs a scatter plot that displays the number of correct answers with and without the calculator for each of the 30 students. The least squares regression line gives us this particular equation here. Which of the following statements is or are true? If we go through point 1, it says here, if the student had used a calculator as the explanatory variable, the correlation would remain the same. The correlation here is R. The one thing you do need to know about regression lines is if you were to interchange our explanatory and our response variable, that would not have an impact on this correlation. It would still be the same thing. So therefore, number 1 is actually a correct statement. Number 2, if the student had used calculator as an explanatory variable, the slope of the least squares regression line would remain the same. Now, all you need to remember about here is slope, again, is rise over run, so we know it's going to be, m is going to be our change in y over our change in x. Well, if they change the explanatory with a response, that means y and x have been reversed. which would make the slope calculation a reciprocal, or really a flip of it, so therefore the slope would have to change, so number 2 is not a correct statement. Statement 3, the standard deviation of the number of correct answers on the paper and penciled quizzes was larger than the standard deviation on the calculator quizzes. Now this one is a trickier question, and you're going to want to reference your formula sheet. If you look at the formula sheet, they're going to say that the slope calculation, another way of knowing that, is equal to R, or the linear correlation, times the standard deviation of y over the standard deviation of x. If we take a look at our slope, which is right here, we can actually fill this statement in. So we would have 0.865 is equal to R of 0.79. And then we would still have S of y over S of x. If you solve for S of y over S of x, just divide by 0.79 on both sides. When you do that, you're going to get 1.09. Now, the only way to get a slope value here greater than 1 is S of y is going to have to be a bigger number than S of x. So in this case, we can clearly say that S of y would be greater than S of x. So now how do you interpret this right here? Well, go back and remember that the y variable in this case is the calculator. The x variable is the pencil. So this would say the standard deviation of the calculator is greater than the standard deviation of the pencil. This statement here says the standard deviation on the paper and pencil was larger. So this case here is actually going to be a false statement. That's a tricky one. Based on that, we clearly can see the only answer that would work would be letter A, that number 1 is only the correct statement. If you're ever in doubt on a multiple choice or free response on this test and you're not sure what to do, I highly recommend referencing the formula sheet and seeing if any of those formulas would help you resolve or think through a question. Question 5 and 6. Scientists examined the activity level of fish at 7 different temperatures. Fish activity was rated on a scale of 0 with no activity to 100 with maximal activity. The temperature was measured in degrees Celsius. A computer regression printout and a residual plot are given below. Notice that the horizontal axis on the residual plot is labeled as the predicted of S/T, which would be fish per temperature. So here we have our residual plot and our computer output. Question 5. What was the activity level rating for the fish at the temperature of 20.4 Celsius? The easiest way to go about this is to first write the equation. So for this, what I'm going to do is look at our computer output and notice that the temperature here is our explanatory variable, so that's our x, and then our response is going to be the rating scale. So what I'll do is write y hat is equal to, our y-intercept is right here of 148.617. The slope is negative, so we're going to be negative 3.21167. And this is going to be times, I'm going to do the temperature here, or our x. So we have our predicting line. All we need to do for this is to actually take the temperature and plug it into our model to see what we get. When we do that, you are actually going to get that it is 83.0. That is our prediction. So now you're going to have to back into what the actual observation was. So remember, the other formula is that our residual is equal to our observed minus our predicted, or our actual minus our prediction, if you want to say that. The prediction here is going to be the 83. The observation, or our actual data, we don't really know yet, but we can look at the residual amount from our actual graph. So remember, our prediction was 80.3, and that's what this is right here. So the prediction of 80.3 is going to roughly be right about here, because this right here is going to be 90, so I would say probably more here. So if we go on to here at about 80.3 and we go up, we can tell this point here would be the residual. If you eyeball it, that residual amount is going to be about 3. So I'm going to put 3 in here for the residual. Well, now we can go ahead and we can solve for the actual or observation amount. Adding 83 to both sides is going to give us the answer of letter A of 86. So this one is actually a little more involved. Be careful about writing the equation first, and then thinking about what they really want to know is what was the actual activity level, not the predicted level, because clearly we see that that answer was there in answer B, which is not correct. We have to actually find that actual or observation amount. Number 6, which of the following gives a correct interpretation of S in the setting? Really all this is going to be is just a definition of knowing what S stands for. Remember, S just stands for the standard error of the residuals. So that would be the standard error or the average error between the actual and predicted. Looking at the definitions here, you're going to notice that letter C, the average distance of the activity level ratings from the least squares regression line is about 4.785 units. Again, this S, or the standard error of the residuals, is a good definition to know and be prepared to either state as a free response or look at as a multiple choice. Number 7, which of these is not true of the correlation R between the lengths in inches and weights in pounds of a sample of brook trout? Now, the one thing you want to remember, if you can, is that correlation technically has no unit of measure. So the one that is not true in this case would be letter B, that it's measured in inches. We do know letter A is true. Correlation is between -1 and 1. If longer trout tend to be heavier, then we're going to see that the correlation is positive in that they move together. As one goes up, the other goes up, which will give us a positive correlation. Letter D, R would not change if we measured the lengths of trouts in centimeters instead of inches. And E, R would not change if we measured the weights of trouts in kilometers instead of pounds. If we do a transformation where we multiply or divide, that transformation will not impact our correlation coefficient. Number 8, when we standardize the values of a variable, the distribution of standardized values has a mean of 1 and a standard deviation of 0. That's the point of doing a z-score. Suppose we measure two variables, x and y, on each of the several subjects. We standardize both variables, then compute the least squares regression line. Suppose the slope of the least squares regression line is negative 0.44. We may conclude what from this? Now, if you're not sure where to go with this, again, that's why I suggest looking at that formula sheet. They're talking here about slope and correlation. One of the formulas you do see is they have b of 1 equals r, which is our correlation coefficient, times s of y over s of x. So the standard deviation of y's over standard deviation of x's. We know here they're talking about the slope, so we could do something like this of the slope. And the key here is if we're standardizing both variables, what do we know about these standard deviations? Well, they just told us the standard deviations would be 1. So R, we still don't know, but we know this would be 1 and this would be 1 because they're both standardized. So because of this, if you solve it, it is guaranteed that we can see R would actually equal negative 0.44. So in this case, letter E is a correct answer. Number 9. There is a linear relationship between the number of chirps made by the striped ground cricket and the air temperature. A least squares fit of some data collected by a biologist gives the model of y hat equals 252 plus 33x, where x is the number of chirps per minute and y hat is the estimated temperature in the degrees Fahrenheit. What is the predicted increase in temperature for an increase of 5 chirps per minute? Well, in this case, what we can get from this problem is that we know chirps per minute is going to increase by 5. Well, chirps per minute is the x value. So all you have to do is actually put 5 in there for x. And the only difference you're going to see is in this slope calculation, really. So if you do 3.3 times the 5, you're going to see that the difference is going to be 16.5, which is going to be letter B. Now, if you don't see it that way, a second way you could do it is you could just put in the 5 here, and you can compute the complete prediction, but then it increased to 5, so you would also do a second scenario with x is 0, compute that prediction, and subtract the difference, and you will still get 16.5. Number 10, a data set included the number of people per television set and the number of people per physicians for 40 countries. The phantom screenshot below displays a scatter plot of the data with the least squares regression line added. In Ethiopia, there were 503 people per TV and 36,660 people per doctor. What effect would removing this point have on the regression line? So if we look for them on the regression line, they're going to be this point right there at the top. Now, if we remove that point, what's going to happen? Well, this point right here is going to be pulling this line upward to where it is. So if we drop this point altogether, what's going to happen is our line is going to relax some, really quite a bit, and it's going to go more like this to represent the points. So what we're going to see is the initial green line that we see with Ethiopia in there is not going to be positive anymore, but it's now going to be negative. So in this case, we are going to see letter C be the correct answer. The slope would decrease, and what's going to happen, the y-intercept we can clearly see is also going to increase at that time. So the y-intercept here is a small amount, and it's going to really just flip. Starting the free response, number 11, Sarah's parents are concerned that she seems short for her age. The doctor has the following record of Sarah's heights. So we have age and height. Make a scatter plot of these data. So don't forget when you do this to actually label your x and your y axes accordingly and have your tick marks spaced out appropriately. Part B, using your calculator, find the equation of the least squares regression line of age on height. So here is the predicting model I'm going to use. If you don't use the actual words in here, you can use x and y, but if you use x and y, you must define what they stand for somewhere on the side. Also, for your response variable, do not forget the hat. This ensures that it is a predictor and not an actual answer. Part C, use a regression line to predict Sarah's height at age 40 years, which is 480 months. Convert your prediction to inches. So one of the things I probably should have done is if I go back to the scatter plot though, we should label this. This height was originally in centimeters, so that's important to have had that. The age is actually in months too, so that is also important. Now, based on that, we can do this problem more accurately. Again, use a line to predict Sarah's height at age 40, so 480 months. So all I need to do with that clearly is going to take the 480 and we will put that in for the age. Make sure to show your work. When you do that, you're going to get 255.934 centimeters. Don't forget your label. You guys be really careful. You cannot just give the AP board a final answer. You must show this step of work. Otherwise, you could get from an E to a P on a free response. They then want us to take this and convert our centimeters into inches. So all we need to do is to take this value and divide it by 2.54. And that's going to give us here, showing our work again, 100.76 inches. Part D, the prediction is impossibly large. Explain why this is happening. So if you take a look at this here, our months are between 35 months to 60 months is our data. So we interpolate whenever we predict our x values in this range. When we're outside of this range, which clearly 480 is called extrapolation. So because we are extrapolating, we must be very careful with our data predictions of anything outside of the 60-month range. Number 12, drilling down beneath a lake in Alaska yields chemical evidence of past changes in climate. Biological silicone left by the skeletons of single-celled creatures called diatoms is a measure of the abundance of life in the lake. A rather complex variable based on the ratio of certain isotopes relative to ocean water gives an indirect measure of moisture, mostly from snow. As we drill down, we look further into the past. Here is a scatter plot of data from 2,300 to 12,000 years ago. What we're seeing here are the isotope values a piece of data have in relation to their silicon values. So part A, identify the unusual point in the scatter plot. Explain what's unusual about this point. Clearly, we should see that this point here in the upper right-hand corner is going to be our unusual point. The value of this order pair might be hard to see the details, but I will tell you is negative 19.3 and 345. So what does that mean? Well, if you look at the pattern here, we have a handful of isotopes that are out in kind of that negative 19 range. What we see that's unusual is it's fairly high. So it's unusual to see an isotope with such of a high silicon level is what makes it unusual. Part B, if the point was removed, describe the effect on the correlation and then the slope and the y-intercept. So if we remove this point, the line that's being drawn here is currently being pulled to that point. So if we drop this point, this line is going to drop. Now, if I had to draw my own line of best fit, excluding that, maybe it would be something of that nature as the line of best fit. What we know about correlation, or the letter R, remember, is two things. It tells us direction and strength. So we know the direction would stay the same. It would still be a negative correlation, but you're going to notice there's less spread out of all the data if this yellow point's not there. It's going to be a tighter relationship, so what's going to happen, you're still going to see the R is negative, but it's going to be a tighter relationship. So it's going to be a negative value, but the magnitude of the number is actually going to increase. So let's say originally the R value was maybe negative 0.5. What we're going to see here is maybe it goes to like a negative 0.7. Now question 2, what's going to happen to the slope and y-intercept? Well, we can tell here the slope of the original line has actually become more steep, and it's going to be a negative slope, so what we're going to see is that the slope will decrease. Then on the other component, if we look at the y-intercept, clearly the y-intercept is going to go from 250 to possibly beyond 350, so the y-intercept is actually going to increase. So we have a decrease in slope and an increase in the y-intercept. Now again, make sure if you were doing this free response question on a test, you can't just say that the slope would decrease and y-intercept would increase. You must give an explanation. So the AP board wants an explanation for every answer that you give them, so make sure to cover that basis. Number 13, long-term records from the Serengeti National Park in Tanzania show interesting ecological relationships. When wildebeest are more abundant, they graze the grass more heavily, so there are fewer fires and more trees grown. Lions feed more successfully when there are more trees, so the lion population increases. Researchers collected data on one part of this cycle, wildebeest abundance in thousands of animals, and the percent of the grass area burned in the same year. The results of a least squares regression are the data shown here. So here we have again the wildebeest in thousands, so we could read this as 500,000 wildebeest, and then the percent of the grass that was burned. So in this case, we had a lower population, higher grass burn, higher population, lower grass burn. Question A, give the equation of the least squares regression line. Be sure to define any variables you use. Remember, if you just use x and y, you must define them. I personally like to use the words within the equation, and it covers it. So when we look at this equation that we have, we see that the slope is the wildebeest per 100, and this is going to be our y-intercept. So when you look at this, you're going to notice that the response variable we see here is the percent burnt. So if we're going to put this here, and this is our predictor, so I'm going to put that, and it's equal to the constant or the y-intercept of 92.29 minus 0.05762, and our response variable in this case, I'm going to put wildebeest. We know is going to be in the thousands. Question B, explain what the slope of the regression line means in this setting. So easiest way to do that, folks, is to really just take this slope, which is right here, which we know is going to be change in y over change in x. So if I rewrite that, I'm going to do 0.05762 over 1, because any whole number will be written as a fraction. The y value here is the percent burned, so I know that's what that means, is my percent burned. And my x is going to be the wildebeest per 1,000. Now I have to be careful, as I notice the slope here is negative and I didn't do that. Okay, perfect. Now let's interpret it. I'm just going to start down here and just say for every 1,000 wildebeest that the percent of the land burnt is going to decrease by 5.762% is how you can interpret the slope. Part B. Find the correlation and interpret this value. As we look at the computer output, be careful, R squared adjusted is not within the scope of this course, but the R squared is. So we have R squared right here. So I know R squared is equal to 0.646. I need to get correlation right here, which is R. So I'm going to come on in and I'm going to take the square root of that. Now if we take the square root of that, we know that R in this case is going to equal either plus or minus 0.803. Now, we have enough information to decide if it's plus or minus. Looking at this equation, we know that the slope is negative. Therefore, the only answer is 0.803 is the appropriate correlation. So again, it's a negative correlation, and we see the data moving in a negative pattern. The magnitude is 0.803, which is a fairly strong linear relationship, which we do see here. Part D, is a linear model appropriate for describing the relationship between the wildebeest abundance and the percent of grass area burned? Support your answer with appropriate evidence. Now there's going to be a couple things you can look at here. The first thing we want to look at is first, do we see the scatter plot? Yes, we have a scatter plot, so we know there's at least a linear pattern. So before you can even talk about is a linear model appropriate, we have to make sure we have a picture of the original data, so we're fine. Now, let's look at the residual plot. We're looking for no defined pattern and some kind of random scatter. So what you could say is for this is that the linear model does seem appropriate based on the residual plot, which shows some fairly random scatter around the residual line. Now, another thing you could comment on, and I will tell you it's popular for the AP board to ask you about R squared, which again is the coefficient of determination, is this here. Another thing you could say is since R squared is 64.6%, we know that 64.6% of the variation in the percent of the grass area burned is explained by the least squares regression line, which is pretty good, leaving about 35.4% of the variation is going to be unexplained by this particular linear model. That's not bad. It's not the best percentage, but at least it's a stronger percentage, and over 50% of it is explained by this particular model.